Okay, so how do we actually solve differential equations with Laplace transforms? So we'll just do a bunch of examples of this. So we want to use Laplace transforms to solve this equation, y prime minus ky equals 0. We already know the solution to this, right? It'll be constant times e to the kt, but we just want to verify that the Laplace transform will actually give us this. So how do we solve this? Well, we take the Laplace transforms of both sides. And we use the linearity of these things. And the Laplace transform of 0 is just 0. So what's the Laplace transform of a derivative? It's s times the Laplace transform of the function minus y of 0 minus k Laplace transform of y equals 0. So we'll gather our Laplace transform terms, s minus k times the Laplace transform of y equals y0. Laplace transform of y equals y0 of s minus k. And we have to recognize when we look at these things what kind of Laplace transforms we're dealing with. We know that the Laplace transform of e to the kt, Laplace transform of a exponential is 1 over s minus k. So this Laplace transform is an exponential, e to the kt, but it's multiplied by a constant. So we know the Laplace transform of y of 0 e to the kt is y of 0 Laplace transform of e to the kt, which is y of 0 over s minus k. So Laplace transform of y equals y of 0 over s minus k. So what is y? Y is the inverse Laplace transform of y of 0 over s minus k. And we know that that is this function here. Which is what we wanted, right? That's what we should get. Good. So how do we solve this? Well, we know what the answer should be, right? It's a homogeneous solution plus a particular solution. So y should be some constant, k1 e to the 3t, that's my homogeneous solution, plus another constant, cosine 5t plus b sine 5t. That's the guess I would make for cosine 5t, plus, well, we'll go ct squared plus dt plus e as the guess that you get for t squared. So that's what the solution to this should look like. And again, does the Laplace transform give us that? Well, we take the Laplace transform of both sides. The Laplace transform of y prime equals Laplace transform of 3y plus cosine 5t plus t squared. And using linearity, that gives us, well, and the Laplace transform of a derivative is SL of y minus y0, which in this case is 1, equals 3 Laplace transform of y plus Laplace transform of cosine 5t plus Laplace transform of t squared. Okay, so that's our linearity. We'll gather all our Laplace transform terms over on the left side. That's this term and this term. The one over to the right side, Laplace transform of cosine 5t is, now I never can remember, the s goes with the sign of the cosine. It goes with the cosine. So Laplace transform of cosine 5t is s over s squared plus 25. And the Laplace transform of t squared is 2 over s cubed. And we got those from our tables that you will be given on tests and stuff. So there's a Laplace transform. So dividing both sides by the Laplace transform of y, and note that this thing here is the characteristic equation that you would get from this homogeneous equation. We get 1 over s minus 3 plus s over s minus 3 s squared plus 25 plus 2 over s cubed s minus 3. So just divide both sides by s minus 3. What should this turn out to be? Well, dig back in your brain and find the partial fractions decompositions. So we have 1 over s minus 3, that's this term. S over s minus 3 s squared plus 25 should be some constant, we'll call it a1, over s minus 3 plus b1s plus c1 over s squared plus 25. So that's our partial fractions decomposition of this term. For this term, the partial fractions decomposition will be a2 over s minus 3 plus b2 over s cubed plus c2 over s squared plus c1, d2 over s, and that would be our, that should be a d2, and that would be a partial fraction decomposition. So looking at this, what we see is that should be an e to the 3t term. This should be an e to the 3t term, because anytime we see s minus 3 in the bottom, that should be an exponential. This is going to be a cosine 5t term and a sine 5t term. That's because we've got this s squared plus 25 in the bottom. 25 is the b squared. And then this again is another e to the 3t term. This is going to be, well, 1 over s cubed is a t squared term. 1 over s squared is a t term. 1 over s is a constant. So we get the correct set of terms, right? We get e to the 3t, cosine 5t, b to the sine 5t, ct squared plus dt plus e. We just have to figure out what these coefficients actually are. So what is the partial fraction decomposition of s minus 3 over s squared plus 25? What is that equal to? That's equal to 3 over 34 times 1 over s minus 3 plus 25 minus 3s over 34 times s squared plus 25. So there's this piece, that's these terms figured out. And then what is 2 over s cubed s squared plus 25? No, that's not right. Sorry. 2 over s cubed s minus 3, right? That's this term. And that is going to be minus 2 over 3, 1 over s cubed, minus 2 over 9, 1 over s squared, minus 2 over 27, 1 over s. Great, so we've got all our pieces together. Now we just need to figure out inverse Laplace transforms. So from here, we can deal with this term first. What function has this as its Laplace transform, well, that'll be 3 over 34 e to the 3t, right? This is the e to the 3t term. This is the 3 over 34. What about this thing? Well, that's a little bit more complicated. We'll put a little bar here. We know that the Laplace transform of cosine 5t is s over s squared plus 25, and the Laplace transform of sine 5t is 5 over s squared plus 25. And so what we need to be able to do is to get those two terms out of this thing. So we'll first separate this. We'll take a 25 over 34 times 1 over s squared plus 25. That's the 25 over that. And then we also have a minus 3 over 34 s over s squared plus 25. So this is good, right? S over s squared plus 25, that's just this. So this is going to come from cosine 5t. So the Laplace transform of cosine 5t is s over s squared plus 25, and then you multiply by the minus 3 over 3/4 to get that. This is a little bit trickier because we need to prepare this a little bit because we need a 5 in the numerator to get the Laplace transform of sine 5t. So I'll take a 5 out of my 25 and leave it with the 34 times 5 over s squared plus 25. And so that is now the Laplace transform of sine 5t. So there's our Laplace transforms that come from that. This, remember that the Laplace transform of t squared, we have to be a little bit careful with, is 2 over s cubed. So this term is minus 1/3 times the Laplace transform of t squared. 1 over s squared is just the Laplace transform of t. And 1 over s is just the Laplace transform of 1. So this is the Laplace transform of minus 2 over 27. Great. So what is y equal to at the end of the road? Y is equal to the inverse Laplace transform of that, which is e to the 3t, plus the inverse Laplace transform of this, which we do by partial fractions. Look that up on Wolfram Alpha, okay? Whenever you need to do partial fractions in the homework, use Wolfram Alpha to get the partial fractions. And that led us to 5 over 34 sine 5t and minus 3 over 34 cosine 5t. So Laplace transform of y is this term plus this term, finally, plus that term, right? And that's here. So these three terms. Minus 1/3 t squared, minus 2 over 9t, minus 2 over 27. And so that's our solution. Oh, and I should have, I forgot, I need this too, which is the 3 over 34 e to the 3t. And then I should also have an s minus 3 term that comes from here, which I've got. It's 2 over 27. Right, plus the rest of those. I apologize for leaving that out. 2 over 27 e to the 3t. Great, so what do we got? We got our e to the 3t. We have three separate terms for that, but we can add those together. We've got a sine 5t, a cosine 5t, and a quadratic, which is what we're expecting up at the top. So notice that the Laplace transform is a little bit automated here, right? You just, use Wolfram alpha to find the inverse, use Wolfram alpha to get the partial fractions, and then that just gives you the coefficients right away. So how about to solve this? What would we think this would be? So here, right, our homogeneous solution is C e to the 5t. What would our guess be? Be a constant times, well, e to the 5t, right? But you have to multiply by t because it's the same as the homogeneous solution. So let's see how the Laplace transform handles that. So Laplace transform of y prime equals, take the Laplace transform of both sides, 5y plus e to the 5t. The Laplace transform of a derivative is s times the Laplace transform of y minus y0. That's our 3 here. And this is 5 Laplace transform of y plus, that's a y, Laplace transform of e to the 5t. So s minus 5 Laplace transform of y equals 3 plus 1 over s minus 5, because that's the Laplace transform of e to the 5t. So Laplace transform of y equals 3 over s minus 5 plus 1 over s minus 5 squared. And note that the squared here when you see that, you should think derivative, right? What's the derivative of 1 over s minus 5? Well, that's minus 1 over s minus 5 quantity squared. And remember that the Laplace transform of t, f of t, is minus d by ds of f of s. So what we've got here is that this term, 1 over s minus 5, equals minus the derivative, 1 over s minus 5 squared equals minus the derivative of 1 over s minus 5. Because we can just move this minus sign here over to the other side. So this thing here is a derivative. In fact, it's the derivative of minus the derivative of s, 1 over s minus 5. So the inverse Laplace transform of 3 over s minus 5 is 3e to the 5t. The inverse Laplace transform of 1 over s minus 5 quantity squared is t e to the 5t. And so our solution is 3e to the 5t plus t e to the 5t. And the t comes from the fact that it's a derivative. So when you see these squares or cubes or whatever in the denominator, that means we're starting to see derivatives. Okay, what about a y double prime plus b y prime plus cy equals 0? What's the Laplace transform of this? And we know what this is. This is the second order homogeneous equation. We know there's 3 cases, 2 real roots, 1 repeated root, 2 complex roots. So why does the Laplace transform give us that? Well, this becomes, we'll just do the linearity right off the bat. And then this becomes a times s squared Laplace transform of y minus s y of 0 minus y prime of 0, because that's the formula for the Laplace transform of second derivative, plus b s Laplace transform of y minus y0, because that's the formula for the Laplace transform of a derivative, plus c Laplace transform of y equals 0. So gathering all our terms together, we get AS squared plus BS plus C. Laplace transform of Y equals SY0 plus Y prime of 0. That's times an A. I need to remember to distribute that A to here and distribute the A to here. Plus BY of 0. That's this B times that. Great. So we notice here, this is our characteristic equation that we've seen before, and we'll see again, right? A squared plus BS plus C equals 0. That's what gave us the roots. This whole right-hand side, I'm just going to call capital AS plus capital B, so we don't have to rewrite all those terms over and over again. So the Laplace transform of Y is equal to AS plus B over AS squared plus BS plus C. Great. And the question is, what's the partial fraction decomposition of that look like? Because then we can turn it back into then we can take the inverse Laplace transform. So case 1, A squared plus BS plus C factors as A S minus R1. There's our eigenvalues, S minus R2. Then AS plus B over AS squared plus BS plus C equals AS plus B, A, S minus R1, S minus R2, and our partial fractions decomposition would make this yet more constants, alpha over S minus R1 plus beta over S minus R2. Right, and if you get S minus R1 and S minus R2, then you get Y equals alpha e to the R1t and beta e to the R2t, which is what you'd expect, right? That's how the homogeneous solutions worked out. So case 2 is that AS squared plus BS plus C has one real root, so that means it factors like that. And remember, at squared, that's going to give us a derivative. So that means that our Laplace transform is AS plus B over A S minus R quantity squared, and a partial fractions decomposition of that would give you this. And this is the derivative of 1 over S minus R. The 2 gives it away. And so that means Y is going to be alpha e to the RT plus beta. The derivative in the S domain means that you're multiplying by T in the T domain. And then we have an e to the RT. And so that gives us that. So case 3 is where you have the two complex roots. But instead of doing two complex roots, what I'm going to do is I'm going to complete the square on this. And so if I complete the square, I get A S plus B over 2A squared plus C minus B squared over A. Great. This part, right, this is actually, if you factored out the 4A, this is the B squared minus 4AC. That part has to be positive, right? Otherwise, you wouldn't get two complex roots, you get two real roots. So I'm going to rewrite this as A times S plus alpha, that'll be the b over 2a plus squared plus beta squared. Great, so that means my Laplace transform of y is as plus b over a s plus alpha squared plus beta squared. And a little bit of tidying, make this a times s plus alpha plus beta minus a times alpha over a s plus alpha squared plus beta squared. And why do I do that? Because I want to rewrite it like this. The exact form of the constants isn't so important, but I need to have an s plus alpha here to match that s plus alpha there. So remember that the Laplace transform of cosine of beta t is s over s plus, over s squared plus beta squared. But if I multiply that by an alpha e to the alpha t, the effect of multiplying by e to the alpha t in the time domain means that you shift in the s domain. So this term, the s plus alpha and the s plus alpha squared, this is giving me, I have to be a little bit careful about my signs, but that's giving me e to the minus, about my constants, right? This a is a little bit of a pain. E to the alpha t cosine beta t. This term, remember that Laplace transform of sine of beta t is beta over s squared plus beta squared. So the Laplace transform of e to the alpha t sine beta t is going to be beta over s minus alpha squared plus beta squared. So this term is going to be k2 e to the minus alpha t. And alpha t, the exponential you can see is because of the shift there that happens in completing the square times sine of beta t. Great, so by completing the square, we get a shift in here, and that shift corresponds to getting the e to the minus alpha t's. And then we have something squared plus something else squared in the bottom, and that gives me the cosines and sines that I want. So Laplace transforms give us the correct answers for solving second order differential equations. So how do we solve this thing? Example 5. Well, you take the Laplace transform of both sides, the Laplace transform of y double prime minus 13 Laplace transform of y prime minus 140 Laplace transform of y equals 3 Laplace transform of e to the 10t. Second derivative, s squared Laplace transform of y minus s times y0, so it's an s minus y prime of 0, but that's 0, so we can ignore it, minus 13 times the Laplace transform of y prime, which is s Laplace transform of y minus y0, which is 1. Be careful with this particular term when you do it in by hand, because the 13 is going to distribute to both of these two parts. Laplace transform of y prime has got two parts. Minus 140 Laplace transform of y equals 3 over s minus 10. So what do we get? We get s squared minus 13s minus 140, Laplace transform of y equals 3 over s minus 10 minus s, plus s, right? Because we move this term over. Oh, plus 13. I forgot this minus 1. So plus a 13. Okay, so we divide both sides. Note that this is the characteristic equation that you'd get from plugging in here. So we divide both sides by that. We get all that. Now note we can actually factor s squared minus 13s minus 140. That factors into s minus 20 times s plus 7. Great. So what do we actually get here? We have three over s minus 10, s minus 20, s plus 7, plus s plus 13 over s minus 20, s plus 7. Okay, so we want to be able to figure out what this is. But we can see right away that we're going to have an e to the 10t term here, an e to the 20t term there, an e to the minus 7t term there, an e to the 20t term there, and an e to minus 7t term there. All the terms involving e to the 20t and e to the minus 7t, those are our homogeneous solutions. Anything involving an e to the 10t is a particular solution. So this is our homogeneous solution, part of our homogeneous solution, and this is part of the particular solution. So we need to know what's the partial fraction decomposition of this, and again, go to Wolfram Alpha and ask it. And what do we get? We get, oh, I have this written down here somewhere. There we go. This is 1 over 90 over s minus 10 plus 7 over 27 over s plus 7 plus 20 over 27, 1 over s minus 20, and s plus 13 over s minus 20, s plus 7. What is that going to be? That becomes 3 over 170, 1 over s minus 20, plus 1 over 157. That's what it looks like, 1 over 157, 1 over s plus 7. And these numbers are correct as long as I can read my own handwriting. So what is y equal to? Y is the inverse Laplace transform of each of those terms. So it could be a 1 over 90 e to the 10t, that comes from here, plus 7 over 27 e to the minus 7t, plus 20 over 27 e to the 20t. And then we get these two terms, plus 3 over 170 e to the 20t, and a plus 1 over 157 e to the minus 7t. So that's my solution, right? The 10t term, that's my particular solution. And then there's my homogeneous solution. And the numbers can all be combined in various ways. So recognizing what a partial fraction is can help you a lot in figuring out what the solution should look like. So what about this one? Y double prime minus 6y plus 9y equals e to the 3t. We know that the homogeneous equation is r squared minus 6r plus 9, which means that we have r equals 3 as our root. So our guess would be e to the 3t, but we already have it e to the 3t. What's our homogeneous solution would be k1 e to the 3t plus k2 e to the 3t times t, because we have a repeated root. What would our guess be then? Our guess should be a t squared e to the 3t times some constant. So that would be our guess. So we expect to have these kinds of terms in our solution. So Laplace transform of y double prime minus 6 Laplace transform of y prime plus 9 Laplace transform of y equals Laplace transform of e to the 3t. So this is s squared Laplace transform of y minus s times y0, but y0 is 0, minus y prime of 0, so I get a minus 1 there, minus 6 times the Laplace transform of y minus y0, but y0 is 0, so I don't need to include it, plus 9 Laplace transform of y equals 1 over s minus 3, because that's the Laplace transform of e to the 3t. So s squared minus 6, should be an s in there, 6s plus 9, Laplace transform of y equals 1 over s minus 3 plus 1. And finally, Laplace transform of y equals 1 over s minus 3 times s squared minus 6s plus 9 plus 1 over s squared minus 6s plus 9. But s squared minus 6s plus 9 actually factors into s minus 3 squared. So we get an s minus 3 cubed plus 1 over s minus 3 squared. Great. So these exponents in the denominator are telling me that differentiation happened, right? So we'll note that the derivative of 1 over s minus 3 is minus 1 over s minus 3 squared. The second derivative of 1 over s minus 3 is the derivative of this thing, which is going to be 2 over s minus 3 cubed. So this term here is 1/2 the second derivative of 1 over s minus 3. This term here is the negative of the derivative of s minus 1 over s minus 3. Great. So what are the Laplace transforms? Well, we know that the Laplace transform of t, there we go. The Laplace transform of t, f of t, is minus the derivative of f of s. So we have to be a little careful about our minus signs. So the Laplace transform of t squared f of t is the second derivative of f of s without the minus sign. So what do we have here? This is Laplace transform of t squared e to the 3t would be 2 over s minus 3 cubed. because the Laplace transform of e to the 3t is 1 over s minus 3. If I differentiate it s minus 3 squared, I get 2 over s minus 3. And the Laplace transform of t, e to the 3t, is minus the derivative of 1 over s minus 3. So it's 1 over s minus 3 squared. So I didn't actually need these minus signs, so that's okay. So y equals what? This term is 1/2 of the Laplace transform of t squared e to the 3t. So that means we've got that as our solution. This term is the Laplace transform of t e to the 3t directly. So we just have that. And we didn't have any e to the 3t term at all, as it turns out. Okay, 2 more examples, right? This is going to be our complex analysis one. Note that here, r squared plus 2r plus 8 is our uh, 4 minus 32 is our characteristic equation. And so our eigenvalues are -1 plus or minus I root 7. And so our homogeneous solution should be k1 e to the minus t cosine root 7t plus k2 e to the minus t sine root 7t plus a guess. And the guess should be at plus b because the right-hand side of our equation is this. So that's the kind of thing that we're looking for. How does the Laplace transform handle this? So Laplace transform of y prime plus 2 Laplace transform of y, Laplace transform y double prime plus 2 Laplace transform y prime plus 8 Laplace transform of y equals Laplace transform of t. Look all these things up. S squared Laplace transform of y minus s times y0, but that's 0, minus y prime of 0, that's also 0, plus 2 Laplace transform of y minus 2 times Laplace y of 0, but that's 0, plus 8 Laplace transform of y equals 1 over s squared. Keep forgetting the s there. And if you do your partial fractions decomposition on that, this becomes where did I write this down? S minus 2 over s squared plus 2s plus 8 plus 1 over 8, 1 over s squared minus 1 over 32s. So there's our solution. This term, we can recognize that as the Laplace transform of t, right? 1 over s squared. So this is a 1 over 8 times t, and this is the Laplace transform of just a constant, right? 1 over s is the Laplace transform of 1, so we get that. So there's our particular solution, 1/8 t minus 1 over 32. So I should do double arrows, right? Laplace transform of this is this, inverse Laplace transform of this is that. So what about this thing? So we have to be a little bit careful about this. First, we'll complete the square on the bottom. We need a complete square, so s squared plus 2s plus 1, right? We'll take the 8 and break into 1 plus 7. That gives me s minus 2 over s plus 1 quantity squared plus 7. So this is beginning to look like a shifted cosine and sine term. The s plus 1 here, a shift in the s domain corresponds to multiplication by an exponential in the time domain. So that'll give us an exponential. To be able to get that to work, though, we'll need to have an s plus 1 in the top as well. So we'll rewrite s minus 2 as s plus 1 minus 3. And now I can break these apart. Again, s plus 1 over s plus 1 squared. And 7, keep in mind, is square root of 7 quantity squared. And then minus 3, 1 s plus 1 squared plus square root of 7 squared. Keep in mind that the Laplace transform of e to the minus t cosine root 7t, what is that going to be? Well, the cosine gives us an s over s squared plus root 7 squared, but the e to the minus t means we shift the s to s plus 1. So that'll give me s plus 1 over s plus 1 squared. The plus 1 comes from the e to the minus t, plus root 7 quantity squared. So that's this term. So the Laplace inverse Laplace transform of that is e to the minus t cosine root 7t. What about this term? Well, the Laplace transform of e to the minus t sine root 7t. Well, the Laplace transform of sine root 7t is root 7 over s squared plus root 7 squared. But the e to the minus t means shift the s like we did here, so it would be an s plus 1 squared plus root 7 squared. So this term is almost exactly what we want. What I need to do, though, is multiply the top and bottom by root 7. And now I have this to look exactly how I want it. And there is our solution. So what is y of t equal to? Y of t is the inverse Laplace transform of this term, and that's e to the minus t cosine root 7t minus 3 to the root over root 7 e to the minus t sine root 7t plus the inverse Laplace transform of these two terms, and that's my t over 8 minus 1 over 32. Okay, great. So last example, mass on a spring, no friction, periodic forcing, right? Do we get beats or do we get resonance here? So, right, we pulled it 1 unit and let it go, and we're going to see what happens. Laplace transform of y double prime plus 49 Laplace transform of y equals Laplace transform of cosine 7t s squared Laplace transform of y minus sy0, so that's just an s, minus y prime of 0, which is 0, plus 49 Laplace transform of y equals s over s squared plus 49. Okay, so s squared plus 49, Laplace transform of y. We get that, and then we divide both sides by s squared plus 49. And we get this. Great. We know what this is, this first term. This is just the Laplace transform of cosine 7t. We look at this, you think, well, there should be a derivative going on here. So what's the derivative of 1 over s squared plus 49? Right? And that's the derivative of, if you like the chain rule, 49 to the minus 1. So it becomes minus 1 times the derivative of the thing inside, which is 2s, s squared plus 49 to the minus 2, which is s squared plus 49, quantity squared in the bottom, right? So powers in the denominator tell me that I've done a differentiation somewhere. Great, so what is this thing? The thing I've got is minus 1/2 the derivative of 1 over s squared plus 49 is s over s squared plus 49. So is this the Laplace transform of something I recognize? Almost, right? If there was a 7 in the top, it would be the Laplace transform of sine of 7t. But constants are easy to deal with. I will just multiply top and bottom by 7. So that gives me a minus 1 over 14 outside, d by ds of 7 over s squared plus 49. So the thing that I want is the derivative minus 1 over 14 times the derivative of 7s over s squared plus 49. And that means that the Laplace transform of this will be 1 over 14 t sine of 7t. So the differentiation minus the differentiation tells me that I've multiplied by t in the, it means that I multiplied by t. So differentiation in the s domain means multiplication by t in the time domain. So what is y equal to the inverse Laplace transform of this, which is cosine 7t, plus the inverse Laplace transform of this, which is 1 over 14 t sine 7t. And that tells me that I have resonance going on there, right? This term is going to blow up. Okay, so Laplace transforms are pretty straightforward. You just have to recognize the partial fractions and then being able to go back from Laplace from s terms back to t terms, the inverse Laplace transform. Laplace transforms also handle types of functions that we have not been able to address yet, in particular step functions and shock functions. And so we will see that next week, and that's where Laplace transforms really can save us a lot of work.